Okay.
One moment.
So
yeah, you have to make sure that everything works.
Mm-hmm.
Okay, so it seems that the stream is on. Let me also start the recording. All right, so I'm happy to present Misha Kornev, who will tell us about some elements of material homotopy theory. Please, Misha, take it away.
Thank you. So we start with some basic notions. So suppose that C is some category with Grothendieck topology, say tau, and we consider the following object in the category of simplicial presheaves on C. So this is just by definition, this is the following set of functors between delta op and presheaves on C as usual. So each UN is a presheaf of sets on C. And consider the following definition. We say that the map from U to V is a hypercover if the following holds. The map from U to V should be a local acyclic vibration. So every Lifton diagram looks like this. Should have a solution, a Lifton, and it can be translated to the diagram, to the following diagram. Okay, and this is a this phenomenon. This phenomenon is a so-called descent, and so we require that there is a solution, some solution. So some solution, of course, after refining. So there exists a solution after refining to some cover. So we require that there exists some family, some cover of X, such that for any I, we have the following Lifton in the diagram. So in other words, you have a solution, not in this case, but after some refinement. by some xi's. Okay. Okay, but of course, there is a more general notion, and now I try to formulate it. So this definition, of course, can be formulated more generally in the setting of different topuses. But once again, suppose that we have some topos S. Sorry. Yeah. No. We have some site. So no. This definition is not the one I said, but what I want to say. Never mind. Skip it. Okay. But of course there is a equivalent definition, which looks like this. So we say that the morphism, some morphism from U to V, say F, in simplicial presheaves on C is a hypercover if for any n natural n the canonical morphism, canonical so-called matching morphism in matching relative morphism in Reed model structure. So this relative morphism over coskeleton n minus 1 coskeleton of V and simplex of it in this category are local epimorphisms. So being local epimorphisms means that you have some this is some technical condition, but you can think about it as just epimorphisms. So in other words, the map F is a really local epimorphism. So this map is induced by the following map in the diagram. So of course, this map from U to V induces the map between coskeletons. So recall that about this coskeleton functor, you can think as about some construction from usual topology when you take a topological space and glue some cells to kill homotopy groups over starting from some n, and so yeah, you have the following induced morphism between coskeletons. And of course, as this one is a pullback, so you have by universal property morphism from U to this pullback. Okay, and this is an equivalent definition of being hypercover. So remark some general remark here. If you have a topos of sheaves over C on C, and if this topos has enough points, then a morphism F is a hypercover. This morphism lives in simplicial sheaves over C. Is a hypercover if all stocks are acyclic confibrations. So recall that a point X of a topos, say E, is a geometric morphism. So from the base space topos set to E, and this is induced. This is a corresponding morphisms, functors, and such that. Yeah, this is just the definition of a point of a topos. But now I give the definition of a topos having enough points. So a topos E has enough points if isomorphy can be tested by stocks. So if the inverse image functor x star of A, the stock of A at X, just a second. Yeah, these functors should be jointly conservative. For all X are jointly conservative. It means that, so recall that a functor is called conservative if, from the fact that f of G is an isomorphism, we get that G is isomorphism 2. Okay, and now example here. Consider the topos of presheaves over some of sheaves on any topological spaces. So is a topological space, and so it means that we should verify something locally, informally, I suppose. Okay, and now there is a fact that if this topos has enough points, then this map is a hypercover if all stocks are acyclic confibrations. So we suppose that the topology, not topology, but the model structure is global projective, and in this case, we get this statement. Okay. Now, the main example of hypercover this example comes from the topology of covariance, usual covariance of topological spaces. Hypercover. So consider the following check complex. So, suppose we are given tau cover. So that the map from U to V is a tau cover. So tau is some topology on our category C Grothendieck topology, and we can form the following simplicial presheave. So UN by definition is the iterated pullback of U over V n time and n plus 1 times. So this definition is some sort of a generalization of the notion of usual check cover. So we get check hypercover U, fancy U to V. The reason why is that in the usual setting of the category consisting of open sets and as morphisms, inclusion morphisms, then then in this category the pullback operation is the same as the usual intersection of sets, and we have a correspondence between these guys and intersections with some open sets. Okay, and here there is a theorem. The closed field localization of the category simplicial presheaves on C with respect to the class of check hypercovers exists, and it is called, we will denote it by L tau by L tau of this simplicial presheaf over C, and yeah, it exists, and prove this theorem. We prove this theorem, model some standard results from model category theory. So for any M left proper combinatorial simplicial model category, and suppose that I is a set of morphisms morphism M. So L, so the Boas-Field localization with respect to I of M exists, and inherits a simplicial model category structure from M. Okay, so we should only verify the fact that the class of tau hypercovers form a set, but it is so as we suppose that C is a small category. So I should say it, but so we suppose that C is a small category. Sorry, oops. Tau hypercovers form a set as C is small. Okay. Now yes, there is another definition. There is another definition of the homotopy theory of tau homotopy sheaves. So we say that this category of tau homotopy sheaves and this category of tau homotopy sheaves, and this the following results due to Jardine and Joyal. But here I want to say that sorry. Yeah,
I'm sorry, I don't quite understand why tau hyperpowers form a set. I don't think that it's correct. I mean, there is this result that you sort of can choose a small set that is so every hypercover is isomorphic to an element of the set, but it's not true in general that hypercovers form a set. At least that's one of the key points in Dagger's paper, that you actually need to find some small set that represents all hypercovers.
Mm-hmm. Not all hypercovers, but hypercovers of this form. Check hypercovers. No.
Oh, check hypercovers. Yes, check hypercovers form a set, of course.
Thank you. Okay. Okay. Now I wanna talk about the Jardine model structure, Jardine-Joyal model structure. This is so this model structure is equivalent to this one. So definition. Suppose that we have a object, some special presheaf on C. V is an object of C, and D and X is a base point. Then define a presheaf of abelian groups Pn by n of X, just by letting that this is a presheaf of ordinary by n and we can sheafify this presheaf with respect to the tau topology. So F being a map being an object in the slice category or over category over V, and let Pn tau be the sheafification of the presheaf by n in the tau topology. Restricted to C over V, and let W tau be a set consisting of such morphisms from X to Y in simplicial presheafs on C such that the induced map as star between these sheaves is an isomorphism. For any V leaves for any object V and for any base point X in X of V. Okay, so this and we can form the following model category structure. Say that W tau and the W tau is a class of weak equivalences. And Obshkov is a class of object-wise vibrations. Okay, so we have a.
Yes, and the definition of W tau, you should also say that it is a bit bijection by zeros.
Yeah, thank you. When n greater than 1 and if n equals 0, then is a bijection. Yeah, thank you. Okay, so we get a model structure on model structure on simplicial presheaves on C, and this model structure is called Jardine-Joyal model structure. Okay, and the theorem by Dagger, Hollander, and Isaacson Dagger, Hollander, and Isaacson. The identity functor is equivalent equivalence between this localization and this localization, Jardine-Joyal localization. So sorry, just model, just Jardine-Joyal model structure. Category with this model structure.
What assumptions do you impose on the category C?
Yeah, thank you. We C is some category with Grothendieck topology, and
I think it should be also a hypercomplete site. Otherwise, check localization is incorrect, and you should do the localization of the whole family of hypercovers.
I'll check it now. Just a second. C is an essentially small category, and that's all.
Well, I'm just certain that Dagger, Hollander, and Isaacson explicitly state that check localization is insufficient. And there are some preprints which mistakenly claim that these are identical, but in fact, in the case of the general site, you have to consider hypercover localization instead of check localization.
Yeah. Okay, thank you. Yeah,
I mean, in practice, almost all sites are hypercomplete, I guess, but theoretically speaking, it's incorrect to state that check localization is sufficient.
Thank you. Okay, and now consider the following example. Yeah. So in particular, a tau sheaf of sets on C. We can consider a tau sheaf of sets on C. View it as a presheaf of simplicial set. Is vibrant, and if tau is subcanonical, subcanonical means that every representable presheaf is in fact a sheaf. Yeah, and if tau is subcanonical, then the Pineda embedding factors through the category of vibrant objects for tau local model category on simplicial presheafs on C. Factors through the category of vibrant objects for the tau local model category on simplicial presheafs over C. Okay, now I want to recall the definition of the Nisnevich topology. The next block. Okay, so suppose that S is a quasi-compact and quasi-separated scheme. So it means that our scheme is good, is good enough, and we can form a category of smooth schemes over S of finitely presented smooth schemes over S. And now the definition of Nisnevich topology. A family of maps So this is a Misnevich cover if each morphism in the family is étal, it means that it looks like some covariant in topological sense. So I won't give the definition, but the intuition comes from the topology of covariance. And for any for any x a point, so for any point here, sorry, for any point here, there exists some alpha and some point y that maps to x. There exists alpha and y from x alpha such that u alpha of y equals x, and also we have an isomorphism between residue fields. Okay, and I'll give an example now. I think, yeah, example. Let K be a field of characteristic characteristic is not zero, is not true, and a some element of K non-zero, and consider the following cover consisting of two maps. The first one is the identical map from A without A to A1, and the second one, this is identical. No, I mean that X maps to X and A1 without 0. In this case, X maps to X squared. Yeah, and these morphisms are étal. This is étal morphisms, and this étal covariant is Misnevich. This étal covariant is Misnevich. If and only if A is a square in field K. So yeah, of course there is another definition by Lurie, but I think I can skip it. And now consider another example. So the risky covers are in particular Misnevich covers. For example, consider the usual covering of P1. And this will be Misnevich. Okay, now define the following fruitful notion, so-called elementary distinguished Misnevich square. So suppose that you have a morphism from U to X and from V to X, say I and P. Then we, and form a pullback U times V over X, and this pullback is called an elementary distinguished Misnevich square. If I is the Zariski open immersion, and P is a tal. And we have an isomorphism of schemes. Okay. And it should be equipped with the reduced induced scheme structure. Reduced means that all stocks of the canonical sheaf of the structural sheaf are local rings without non-zero nilpotent elements. So this is some technical information. So lemma these data consist of I and the morphism P, some morphism P from V to X is a Misnevich cover of X in the above statement. So in this definition, sorry. In this definition, this statement, we have the following statement that this covering is a Misnevich cover of X. An example of non-elementary distinguished square. So this is a non-example. this non-example coincides with the previous example of Nisnevich cover. So you can consider this cover, and this is not an elementary distinguished, and this cover doesn't come from the elementary distinguished square. Sorry. In the case when a equals 0, of course, but when a is not 0, then this is true. So in this case, we have this cover doesn't come from an elementary distinguished square, but so just replace, I just replace this by a, and this does not come from elementary distinguished square if a equals 0, and otherwise, so in the case when a does not equal 0, then it is so. Okay, now we can form the category of spaces. So put tau equals the Nisnevich topology, and in this case we get the Nisnevich local model category. Denoted by L nis. So C in this case will be the category of smooth schemes over S. And recall that S is supposed to be quasi-compact and quasi-separated scheme. And so we will denote it by spaces over S. The fibrant object of this model category will be called spaces. So a space is a presheaf of concomplex on SMS. A space is a presheaf of complexes on the category of smooth schemes, which is a sheaf which is a sheaf in Nisnevich topology. Okay. And now a tool for verifying Misnevich vibrancy in practice. A tool for verifying Misnevich vibrancy in practice. Proposition. Let S be a theorem scheme of finite Gruel dimension. Recall, it means that you have a finite chain of subschemes or closed sets in that scheme. A simplicial presheave F on the category of smooth schemes is Misnevich vibrant. If and only if for any elementary distinguished square the natural map is a weak equivalence of simplicial sets of simplicial sets, and also f of empty set is a final object. Okay, now we are ready to give the definition of A1 homotopy category. Definition. Let I be the class of maps so consider product with a fine line in the category of simplicial presheaves on smooth schemes over S localized by hypercovers. Check hypercovers where X ranges over all objects of the category SM over S, and choose a subset, say J in I, containing such maps where X ranges over a representative of each isomorphism class. Of the category of smooth schemes over S. Yeah. So we fix some notations. I is the class of such maps, where X ranges over all objects of X is any smooth scheme over S, and we choose a subset in I containing such maps in which X ranges over representative which isomorphism class in this category. In this setting, we said that the A1 homotopy theory of a scheme S is the left Bose-Field localization with respect to J. And we will denote it as LA1 of L nis of simplicial presheaves of SM over S. Localization of L nis simplicial presheaves of this. Okay, and consider the homotopy category of this category. We will denote it by this LA1 of etc. is spaces A1. Is called the A1 homotopy category of S. Okay, now the proposition. The Bose-Field localization exists. It easily follows from the fact that simplicial structure, left properness, combinatorial stuff are inherited by the category of spaces over S. So this is simply this proof is, I think, simply that the previous one, and now So we have a definition. We have a definition of A1 homotopy category, and now this is a point when we can. But I want to mention some facts. Just a second. Let me give a remark. A simplicial presheaf X. So this is a object here. Is A1 space if it takes values in CAN complexes. So it means that it is vibrant. It is vibrant in the category of simplicial presheaves. The second point, it satisfies Misnevich hyperdescent that is, it is vibrant in the category of spaces over S. And the last one, if we have a weak equivalence between X of U and X of A1 cross U, so we can think about it as a segment. So our localization gives us a way of thinking about A1 as a segment, and we can contract it. Is a weak equivalence of simplicial sets for any U in the category of smooth schemes over S. Okay, and the next remark that so I don't think that I should write it down, but anyway, one can construct the pointed version of the category of A1 homotopy category, A1 category of A1 spaces. Okay, I write it down. So we have an adjunction between this category of spaces and the category of spaces with some the category of pointed spaces, pointed A1 spaces, and how it works. We take a presheaf and maps it and map it to the presheaf X plus the pointed presheaf of spaces obtained by adding a disjoint base point. Okay. And now we say that the weak equivalences in the category of A1 spaces are called A1 weak equivalences or A1 local weak equivalences. And the next definition is about the homotopy between two maps. Let F and G be maps of simplicial presheaves. We say that F is homotopic to G, or FG are homotopic. A1 homotopic. If there exists a map, say H, from F cross A1 to G, such that the composite of H and this morphism equals F, and with this one equals G, where I0 and I1 are respectively inclusions of points 0, 0, and 1 into the affine line. Okay. So now we're ready to define and discuss some properties of homotopy invariant presheaves with transfers, but I think that we have no time, and I think that we can do that next time. What do you think about it, Krisha?
Yeah, definitely. I mean, it's your call ultimately. So if you think that's best, that's what we should do.
Yeah,
okay,
this is a.
Yeah.
Yeah, this is a point in which I guess we can stop, and it is natural to do that. Okay.
Okay, thank you so much. Let's thank the speaker. Okay, are there any questions, suggestions, comments? Okay, let me stop the recording.